Hey guys, welcome back. Today I'm just going to do a review video on the functions of enzymes, which is what we talked about last class. And so this is just a recap of those topics. So we have them available in video form. So enzyme functions. Right? First, we have to look at the general principles or properties of enzymes. So all enzymes are proteins and they are all catalysts. Right? And so a catalyst is a molecule that will speed up the rate of a specific reaction, but it does not in and of itself get used by that reaction. Right? And so when that catalyst, in this case the enzyme, is in the presence of the molecules required for a reaction to occur, that reaction will happen more quickly than would have without the catalyst around, right? But then that catalyst is just the same as it was at the beginning. So it can go off and find the molecules and cause another reaction, right? Um, the enzymes cannot make reactions that would not occur naturally happen, right? So these reactions do occur on their own. It just makes it happen a lot more quickly. Okay? So looking at how enzymes actually mechanically function, we have to look at the properties of reactions that they manipulate in order to speed up the rate of those reactions. Okay. So as a general concept, when we are looking at chemical reactions, we have to understand that molecules will naturally shift from a high energy conformation to a lower energy conformation. Right? So molecules are more comfortable the lower energy they are. Okay? And so when they have the opportunity to go from some high level state to a lower energy level state, they will take that opportunity and spontaneously shift towards that lower energy conformation. Right? And so here I have modeled one example of a imaginary molecule. Right? This doesn't represent any real molecule, it's just shapes. Right? But it does show the idea of the high energy versus low energy conformations that the molecules will take. And so in this particular molecule, right, we have three different elements all bound. It's actually four because there would be one right here too, but let's ignore that for the sake of the storyline. Right? And so this is the same molecule regardless. It's square, triangle, circle, square, triangle, circle, square, triangle, circle. Right? And so the molecule will exist in all of these conformations regardless. Right? It's always shifting. They're not solid state things. They are fluid. Right? So they're moving all the time. Molecules are. They're either vibrating a little bit or they're moving a lot, right? But they're shifting around. They're not stuck in one shape. So this is constantly moving. However, this middle conformation is a lower energy conformation. It's more comfortable, right? The elements have more space between them. Right? And so there is a negative repulsion between elements because of their electron clouds. And so they try to get as much space as possible as a general principle. Right? And so bigger elements require more space, small elements require less space. Right? But as a general principle, elements will try to get as much space as possible between them. Okay? And that will be a lower energy state. So this is a higher energy state, this is a higher energy state. And so on average, most of the time, the molecule. So as I think I was saying, this molecule is constantly shifting between these states, but most of the time it's in this low energy level state here. It's where it's most comfortable, right? So if we're looking at the reactions, right, if we put molecule A and molecule B together, when molecule A is in this comfortable state, they're not going to react. Right? This guy's like, I'm cool the way I am. I don't need you. Get out of here. So no reaction. However, if they happen to bump into each other when molecule A is in one of those uncomfortable high energy states, right, it is more likely to react with molecule B. Right? This reaction site's now available. This molecule is not comfortable the way it is, and so it's open-minded to receiving this guy's reaction advances. Right? And so they bump into each other, bump, 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 and then this element will engage with this reaction site. Okay? And the resulting conformation is now a more comfortable state for both of these molecules than the starting states were. Right? And so that's what leads to this reaction occurring. So this triangle is bumped backwards into the background here, so it's no longer uncomfortably close to this guy. These guys have stretched out, so they're not bent up anymore, so now they're more comfortable, and this is a pretty happy molecule. Okay. So this is a higher energy state than these two things individually, but in this moment, this is a lower energy state than these two. Right? So the reaction depends upon the two molecules bumping into each other within that high energy state. And that's happenstance. And so that will randomly occur occasionally in nature, just by chance. But the rate at which the reverse reaction happens will be higher. And so you won't see like spontaneous generation of that AB molecule on its own. However, if you blast those molecules with a bunch of energy, they're going to be moving more frequently, right? And so they're going to be shifting conformations more frequently. That triangle is going to be bouncing up and down more frequently, which means that the two molecules are much more likely to bump into each other at a moment where that conformation is uncomfortable and it's willing to do the reaction. Right? And so the amount of energy you have to shove at the molecules to make them react at a constant and steady rate is called an activation energy. Right? And so you start a specific energy level. These are the two molecules separate from one another in that comfortable energy state. Right? You shove a bunch of energy at them, and they get into this high energy uncomfortable state, this transition state. Right? This is when they're in that uncomfortable conformation. So you have this high level energy. Right? So in this moment in time, those two molecules are willing to react to bounce down to the combined, more comfortable molecule state than the transition state. So if you look at the two states, like this one is still higher than that one innately, but it's lower than this one. Right? So it's willing to go down that gradient. It's always trying to get to a lower energy state. So it goes, whoop, hello, thank you. Okay? So that's the activation energy. So I'll go boop, boop, choo. Now, different reactions have different amounts of activation energy. Right? And so the more comfortable the molecules are to start, the more activation energy they're going to require to make this reaction occur. So what enzymes do, what they manipulate, is that amount of activation energy required. Okay? So the enzyme has a very specific shape that is geared towards interacting with the substrates, the molecules that are getting put together or ripped apart. Okay? And so you'll have this active site that has exposed functional groups of the amino acids within this protein that are chemically favorable to engaging with this specific molecule. Right? So this active site will grab A. So what's going to happen is once that molecule A is engaged in this active site, it's going to change the shape of the enzyme. Right? The enzyme changes shape, okay? And that new conformation of that enzyme forces molecule A into the uncomfortable conformation. Right? So this little thing popped up. Right? It has functional groups that the triangle doesn't like, so the triangle runs away from those functional groups, and that pushes this triangle into this uncomfortable conformation state. Okay? This active site is now shaped properly to grab molecule B, okay? And it lines molecule B up very precisely with that reaction site. Okay? So it's forcing this reaction to occur. Okay? And so it's putting everything in just the right place and just the right shape so that this reaction is now favorable, right? It's forced the transition state. So this is an uncomfortable high energy level situation. The two molecules will undergo that reaction and bond to one another. The enzyme will then go back to its original shape and release molecule AB. It can then go back and find another A, find another B, shove them together again, and just rinse and repeat over and over and over again. So by forcing the molecules into that transitional conformation, the enzyme reduces the activation energy required for this reaction to occur. And that in turn speeds up the rate of the reaction. Right? And so it puts them in just the right way, forces them together, and then lets them go. Speeds up that reaction. Right? Enzymes can also break down molecules using the same mechanism, but like basically reverse. Right? So it will grab a molecule that's comfortable in a happy state. Right? So this active site will be geared towards grabbing this molecule. The enzyme will change shape and force that molecule into an uncomfortable high energy conformation. That molecule will respond by breaking off some of those really contorted bonds, right? So this bond is a really uncomfortable angle, and that's too high energy. So it's just like, forget this, and it breaks that bond. And now you have two molecules, right? So these two this substrate has been broken down into two molecules. They are released, enzyme goes back to its original shape and can go through the whole process again. So enzymes can build molecules through reactions, and they can break down molecules into smaller molecules through these reactions. Either way, it's doing it by manipulating the activation energy, right? By forcing these uncomfortable conformations within the molecules and getting them to line up properly for the reaction to occur. And that's it. That's how enzymes work. So, yeah. Bye.